Hello, today for this practical we are going to model this sheet metal forming problem, only this first part. This is an animation I found on Wikipedia. I found it very interesting. So you see that the thin metal sheet is being pushed down by the indenter, is held against a base, and then because of plastic deformation, the metal sheet stays in this deformed, more or less in a deformed shape, with a small amount of elastic spring back after unloading. And the loading was controlled perfectly such that after spring back you have a right angle here. So today we are going to try to use abacus and try to reproduce this right angled hook. So here the problem would have two nonlinearities. One is a contact nonlinearity, which we already seen last week, and the other one is plasticity, which we've learned this week. Before we go straight to modeling, there is some important information that I would like to highlight, which is about the definition of strain and stress when it comes to modeling plasticity. In the lecture, we've talked about all the theories of flow theory of plasticity, but limited to small deformation scale. In the end, I introduced about the concepts of large deformation plasticity and the things to take note there. So in large deformation plasticity theory, the very first thing to look for is the definition of stress strain rates. I mentioned briefly that it needs to account for large rotation, and technically it is called the so-called framing indifferent definitions of stress and strain rates, or the objective stress and strain rates. These concepts do not matter when we only model small deformation problem, but they become very important when we move on to geometrical nonlinear cases, which is the case of our problem today. This is a document that I extracted from Abacus manual. You can give it a more detailed read, but the thing I would like to highlight is that most of the time a stress strain curve that we obtained from an experiment is presented in terms of nominal strain and nominal stress. They are the engineering strain and engineering stress respectively. However, they are not the best suited choices for large deformation plasticity modeling. A few things to highlight: the plastic deformation is nearly incompressible, and engineering stress and engineering strain, they are the same as nominal and the nominal stress and nominal strain. For finite deformation plasticity, Abacus uses different stress and strain measures. d epsilon is an increment of strain. So this is already in a rate form. So if you divide d epsilon by dt, you get the strain rate. But take a closer look at this one-dimensional expression. dl is a change in length per unit time per dt. L is the current length, and L0 is the original length. So in the engineering strain definition, this d epsilon would equal to dl over L0. But look at this expression here. We have replaced L0 by L, the current length. If we sum up all the d epsilon and we obtain the total strain, it would equal to this expression. This is different from the engineering strain definition, where we have L minus L0 divided by L0, but here we have a log strain. This is so-called the true strain. And similarly, we have the true stress, which is basically our Cauchy stress. It's force divided by the current area. So in Abacus, when you define plasticity, you need to provide the true stress and true strain. So they are not directly available for most of your experimental data. And you need to do the transformation. And these are the formulas to transform from nominal strain to true strain So you can use this formula. Derivation is shown here. And we can use the incompressible property of plastic deformation to find the relationship between our true stress and nominal stress. And here we can further relate it to with the engineering strain which we obtain from experimental data most of the time. And then using this equation and together with the one relating strains, we can then transform our experimental engineering stress strain curve into the true stress strain curve that we need for defining plasticity in Abaqus. So this can be easily coded in a Excel sheet, and then you can basically take the values of this curve and then reproduce it into true strain, true stress curve. Here Abaqus has given us an example. These are the nominal stress and nominal strains. This is at the yielding level for steel. And you can see that when the strain is small, there is not much difference. But when the strain becomes large, you can see the difference is significant. The plastic strain here is a scalar measure. So remember that in the class, we have plastic strain being a tensor. It should have 6 unknowns, but we have simplified the problem, the plastic strain, into a plastic multiplier lambda and the direction m. M is in this case the tensor, and lambda is a scalar. And here this plastic strain corresponds to our lambda. Yeah, these are the things I would like to highlight on this document. It is already uploaded on Brightspace. Now we look at this problem. We try to model this, and we can see that this loading in this indenter can be simplified into just a triangle, and we could simplify the base into a symmetric notch-shaped base. And here I've drawn the geometry and given some dimensions, and we can reuse the material properties here provided by Abaqus in this table. And the objective here is to model this shape forming process and form a right angled hook. So before we immediately jump into creating this model, we can look at ways to simplify our model. So this geometry doesn't look like a symmetric geometry, but if you do a free body diagram and you imagine that this is being pushed down and there is a single point in contact, and you can effectively take only half of the model, because so if you take the same length to the left, and this whole part would move up and it will be free from any loading. So this entire part is actually just for showing. So we can model this problem as a symmetric problem with a symmetric boundary condition on the left edge, and we only model the right part of it. So we are going to do this. Let's create the part. Now, before we go ahead, only this plate is deformable. The base and the indenter, they are rigid. There are default ways to create rigid bodies, so-called discrete rigid and analytical rigid. For education purposes today, I would like to illustrate a third way of creating a rigid body, which is more generic. It allows you to create arbitrarily shaped body without any constraint. So we're going to still select deformable, and then 2D. We are doing a two-dimensional problem, plane strain, shell, and we rename this as we create a base first. And the base, we create only this part. So we have this bottom width being half of L2, which is 12.5. Height is 25. Let's create a rectangle first. Give it a dimension 12.5 and 25. Oops, I accidentally clicked it, enter, so we can modify it. 25. Now we can create that notch. So this notch, the height would be h1, which is 15. The width is half of L1, which is 5. We just create dotted lines connected. Click escape, and then we add the constraint, the dimension. This is 5, and then the 1. This is 15, and we have created this notch, and we need to remove the 2 edges. Auto trim here, and we are done with the base. Click done. Now we create another rigid body. No, we don't need to create the rigid body, because when we model a symmetric problem, we can simply model the effect of the indenter loading as a point load. So we only need to create the deformer body, so this part of the plate, which is 2 mm in height and 10 mm in length. So this is the plate to the deformable shell, and we give the dimension 10 in length and 2 mm in height. Click done. So we have created the geometry of the 2 parts. Now let's expand it to see all the components, and now we create the material. This is a steel material. We give it the elastic. The Young's modulus is provided in this datasheet. So you can simply take this stress divided by this strain, and you would obtain a value of and let's give a Euro-Poisson ratio of 0.3. So we've defined the elastic property of the steel, and then of course today we are here to model plasticity. So here we need to give yield stress and corresponding plastic strain. The very first one should always be the initial yield stress with a corresponding 0 plastic strain, and then gradually we fill in the other terms to represent the hardening behavior. So they would correspond to the true stress here, this column, and the plastic strain in this column. So we can either manually key in this, or we could export this in a text file, which I have already uploaded on Brightspace, and then use the read from file of Abaqus. So I have already created this text file. So these are the true stress, and these are corresponding plastic strains. So we can ask Abaqus to directly read from this file. And remember to click here on the left, I don't know, so click on the left Yes, it's here. So then it imports. Take note of the units. So this should be in megapascal. So by default it's isotropic. There are other options, and we mentioned about kinematic and combined. Kinematic is more relevant for cyclic loading, and you can use the others for different material, and also you could define your own with a user subroutine. But for this, we have unidirectional loading. We use isotropic. Okay, after defining the material, we can define a section, steel section, homogeneous. We leave the default thickness to be 1 for plane strain, and we allocate to both the base and the plate. So even though the base is rigid, we still allocate the section, and we do the rigid constraint afterwards. Section assignment, still. Now, then we create the mesh. For the base, this is a rigid body, so the mesh itself doesn't really matter that much, but since we have a contact problem, you may want to control your mesh a little bit. So you may want to have some higher number of elements to see how it goes. You could also have bias. Right, so you have a biased mesh towards the center. Here the biased is, we can flip the biased. Maybe we can reduce it and then mesh it. Okay, so we have created the mesh for the base, and then for the plate, the mesh would matter. We want to seat the edges. So this is the thickness direction, and it involves bending. So we could allocate 2 elements across the thickness and no bias. 2 quadratic ones, so that we avoid the shear locking. And the thickness is 2 millimeters, and we can make use of the size so that we know as a guideline that how the elements would look like. And we mesh it. We have a nice structured mesh, and then very important, we need to change element type. By default you have a reducing equation, and this is not what you want, but before we do this we switch to plane strain. And linear elements, if we uncheck reducing equation, would usually lead to locking, shear locking. We could choose quadratic elements, and because our problem has a point load, we don't want to use reducing equation. Okay, so now the element type for the base doesn't matter that much, because eventually we'll transform this whole thing into a rigid body. Now we go to, so we need to put the 2 parts under instance, so that we assemble them, plate, and then we need to translate one on top of the other. So there are different ways. We can first translate this on top here. Okay, then when we translate it again, but this time we are going to use a different method. Constraint edge to edge. Yep, so now it's shifted to the left. So this is where they are on the same axis. This is where we want it to be. Now, after putting the two under assembly, we can start to define boundary conditions. And before that, we should create the step. So because this is the geometric nonlinear problem, we turn it on. Here we have plasticity. We might want to use smaller increments. And yeah, we'll leave this here. Again, in the first exercise, we learned the influence of this option, and I would like to turn it off so that we use the real full Newton. And then we go to create our boundary conditions. So we have symmetric boundary condition. We fix the base. So in the initial step, we select the left edges, we give them symmetric boundary condition, and these need to be fixed. Then we fix the bottom. This U2 and the rotation is to be fixed. So we have defined the boundary conditions, and we need to define loading. For this problem, we are pushing it downwards, and to have a right-angled hook, the first estimate would to imagine that now enable, if this is a thin sheet and we do not consider the thickness, the downward displacement would be half of L1, which would be 5. Create our loading, and the loading displacement, and we are applying the load on top, and then this will be -5, and we have defined our loading. But for this problem, we also need to define the contact between the two parts. We could use the general contact, but to save some computational time, let's define the surfaces and then define the contact pairs. So we go to surfaces, geometry. The base is the top surface. We select the top surfaces, which would potentially come into contact with the plate, and similarly for the plate, we select the bottom surface. Now, after selecting this, we define our contact, which we define under interaction. So we can use surface-to-surface contact, or we can also use general contact. In fact, let's use general contact, because last time we did not use the pairs under general contact. Last week we used all with self, but I would like to show that we can also use the pairs. So we can use select base top and plate bottom, click, and then click OK. We need to define the contact property. And similarly as before, we select frictionless. Normal, we leave it as default, so it will be the penalty formulation. And then we are done with the contact. Now, we have not yet constrained the rigid body motion. So this base is supposed to be rigid body. So let's go to constraints. So under interaction, we can already have this constraint, I believe. Yeah, create constraint. Before that, we need to create a reference point for this rigid body, and let's pick this reference point. So this will be the reference point which represents the entire rigid body motion. and then we can create the constraint. So we call it rigid body base. Here you can click body, select this entire base, and then reference point, pick the one that we defined, and click OK. So this would impose constraint on all the nodes and constrain all the degree of freedom to this reference point. And now we have defined our rigid body as well. And we need to define an extra step to allow elastic unloading after the deformation. So basically, after making the hook, we want to be able to use it, and for that we remove the loading, we remove the indenter, and after we remove the indenter, this deformed metal sheet would spring back a little bit. So we need to create an extra step, call it unloading static general. For this we expect very linear behavior, so we can leave everything unchecked. And the thing to do in unloading is to simply remove the loading, deactivate loading, and then we are good to go. We have defined everything, defined the contact, boundary conditions, loading, material properties, rigid body motion, plasticity, element types, and the unloading step. Let's create a job. Let's call it PC5 trial 1. Okay. So no error in the input file, and the analysis about it. Let's have a look at the error message. Time increment is less than the minimum, so it's most likely a convergence issue. The solution fails to converge. Alright, so let's have a look at the solution. Right, so it bends underneath, and let's have a zoomed view. So note that the rigid body has no stress. So we have stress concentration. When we say stress, let's check the plastic equivalent plastic strain, which is our lambda. You can see that we have a non-zero plastic strain already, so there are already plastic deformation. And we can check our contact pressure. So contact pressure, there is some highlight here, and we do not seem to, yeah, so there we don't have a contact at the moment. So the contact is only happening here. But you can see that we have some interpenetration. It's due to the penalty formulation that we use.